Hello and welcome to this video on determining whether a relationship expressed as a map or a set of ordered pairs represents a function. Alright, so if you've been following, if you've been seeing previous videos of mine, great. This is a little follow-up to some of those. We've been talking about relations. A relation is a correspondence between two sets, and we've shown how to to represent a relation as a map, which is also known as a mapping or an arrow diagram, which you'll see a couple examples here of a mapping to represent a relation, or a set of ordered pairs, where you also see the relationships between two sets, between elements of two sets, and we'll see a couple examples of that in this video as well. And we're asked to determine whether or not a relation expressed as one of these things represents a function. Right? So I'll talk about what that means here in a second. Alright, so my first example. Right, determine whether the relation is a function, and if it is, right, if so, state this function's domain and range. Alright, so first off, what is a function? So I'll write that off to the side here. So big note, huge note here, right? It's very important. A function is a relation. Okay, so this correspondence between two sets, like I'm seeing here. I see I have the set of friends, and over here a set of birth dates or birthdays, days of the year. And we have a correspondence between them, relationships between them that are pointed out in these arrows. Right? This is what they call a map or a mapping. But a function is a relation. Okay, so it's a correspondence between two sets in which each element of the domain Alright, now we've talked about this in other videos. If you're seeing this for the first time and you haven't seen my other videos, what we've stated what the domain is. The domain is simply a set of all the inputs, or it's a set of all the elements from the first set that actually correspond to elements from the second set. So in this particular picture, Max corresponds to an element over here, Alicia, Trent does. There's arrows coming off of every single one of these names. So Max, Alicia, Trent, Yolanda, Wanda, and Elvis all belong to the domain of this relationship. Right? So it is a relation in which each element of the domain corresponds to exactly one, only one, exactly one. Big thing there, alright? Exactly one element of the range. Alright, and again, this is huge. The definition of a function. Alright, so the range are elements of the second set, right? This set of birthdays over here, and an element is in the range if it actually depends on an element from the domain. If there's an element of the domain that actually corresponds to it, then it belongs to the range. So basically in this picture, in this mapping, if it's at the end of an arrow, alright, so January 20th C is, March 3rd is, July 6th is, November 8th is, at the end of a couple arrows, and January 8th is as well. So January 20th, March 3rd, July 2nd, November 8th, and January 8th, all of these belong to the range of this relationship, this relation between the sets of friends and the set and birthdays. Alright, so let's see if this definition is satisfied though. Alright, so each element of the domain, right, each input corresponds to exactly one element of the range, goes to one output. So in a mapping, what that means is every element in the first set has only one arrow coming off of it. It has exactly one arrow coming off of it. So at least I'll write that out. Right? So in a mapping, what this means is this. Right? So in a mapping, this means that each member of the first set has exactly one arrow coming off of it. All right, and let's see, is that happening here? Yeah. Max has the one arrow coming off. It corresponds to only one element in the range. That's November 8th. Alicia has just one arrow coming off. Corresponds to the January 20th, and that's it. Trent corresponds to only one element, the March 3rd. Yolanda corresponds to only one element, the November 8th. Wanda corresponds to only one element, only one arrow coming off of Wanda there, the July 6th. And Elvis corresponds to only one element in the range, the January 8th. So yes, this relation satisfies the definition of a function. So I'll write that down here. So we say that, so for this particular example, yes, this relation is a function. Great. And then it was stated, hey, if it is a function, state the domain, state the range, and again, the domain is all the elements of the first set, all the members of this first set that actually have an arrow coming off of it, right, that actually correspond to an element in the second set. And the range is all the elements of the second set that have an arrow coming into it, right, that actually are corresponded to by an element of the first set, or that depend on an element of the first set. All right, so the domain here, the domain of this relation, of this function, now we know it's a function, is the set of, again, all the elements in the first set that correspond to elements of the second set. So just all these people, right, all these friends. Max is in the domain, Alicia is in the domain, Trent, Yolanda, Wanda, and Elvis. All 6 of those people, and then close the set, right, belong to the domain of this function. Then the range is going to be made up of birth dates, right? So any birthday that actually has an arrow coming into it, or any birthday that corresponds to a friend, the birthday of a friend, belongs to the range. And we're seeing that all these dates, all 5 of them, would then belong to the range, right? So we got January 20th. I'm going to kind of abbreviate. Sorry, this is January 20th is in the range. March 3rd is in the range. July 6th. November 8th, comma, and then January 8th. All five of those dates, close the set, are in the range of this, what we now know as a function. All right. Great, but this is huge right here, right? This bubble off to the side. The definition of a function, right? A relation in which every element of the domain corresponds to exactly one element of the range, right? So no more than one, no less than one, exactly one, right? And again, in a mapping, that means on this first set, every element, every member has exactly one arrow coming off of it, and not more than one, not less than one. Great. So here's another example. Or I'm not going to have as much writing. Sorry, this is a pretty busy page here. So there's another example of a relationship between two sets, a relation, and that is represented by another mapping. And I'm asked the same thing. Okay, I'm going to say, I'm saying determine whether the relation is a function, and if it is, state its domain and its range. So here I have, again, two sets. This set of numbers and this set of numbers have a relationship between them. These numbers represent, calories per serving of, certain cereals. And this set of numbers, the 16, 18, 23 here, represent sugar content in grams. So all these arrows are saying is that, there's a cereal out there. I don't know what brand. I don't mention any brands here. But there's a cereal out there that has 170 calories per serving that also has, 16 grams of sugar in it, right, in a serving. So there's that relationship. And then there's a cereal out there that has 200 calories per serving that has 18 grams of sugar in that same serving. And then there are, look at this, there are two cereals out there with 210 calories per serving that we're looking at. One of those cereals has just 16 grams of sugar in a serving, whereas the other cereal that has 210 calories per serving has 23 grams of sugar. Okay. Alright, so having looked at these relationships here, the relation between, numbers of calories per serving and number of grams of sugar, the question is it a function? I'll refresh your memory again. Here's the definition. Right, a function is a relation, which we have, right? We have a relationship between two sets in which each element of the domain, right? The domain here would consist of 170, 200, and 210. Each one of these elements in this set actually does correspond to an element over there. Corresponds to exactly one element of the range. Let's see if that's happening. Now the range consists of 16, 18, 23. Every single one of these is corresponded to by an element over here. Well, let's see. So 170 corresponds to just 16. That's good. 200 corresponds to just 18, right? Exactly one arrow coming off of 200. That's good. The problem here is with the 210. Right here, you see how this 210 has two arrows coming off. So, 210 in the domain does not correspond with exactly one element in the range. It corresponds with, two elements in the range, 16 and 23. So by that reasoning, right, this relation here does not satisfy the definition. So this relation, okay, this relation between these two sets is not a function. And since it is not a function, right, I don't have to state the domain and range. That was just part of the exercise. If it is a function, give me the domain and range. I mean, you could still state the domain and range of the relation. It's just, those are not the domain and range of a function this time, right? Domain would be 170, 200, 210. The range would be 16, 18, 23. It's just, again, those are not the domain and range of a function this time. They're just the domain and range of a simple relation. Okay, so those are a couple examples where a relation between two sets was, represented by a mapping or an arrow diagram. Sometimes these are referred to as, for obvious reasons, right? There's all the arrows all over the place. In my last two examples, I have relations that are represented as a set of ordered pairs. All right. So here I have a set of ordered pairs, and in a relation, if you see a ordered pair, usually the first is represented by the variable x coordinate and the second y. When you see this ordered pair, this means that x corresponds to y. Right? Values in the first position are in the domain. Values in the second position are in the range. Right, so that means x corresponds to y. You could also draw an arrow diagram, which I'll do pretty quickly in a second here. But so here's a relation, saying that it's between one set of numbers and another set of numbers, where -3 in the one set corresponds to 3 in the other set. -2 in the first set corresponds to 2 in the second set. -1 in the first set corresponds to +1 in the second. 0 in the first set corresponds to 0 in the second set, and 1 in the first set corresponds to 1 in the second set. Alright, now the question again is, is it a function? Now, when you were looking at a mapping, the only thing you needed to do to determine if it was a function is you looked at all the values in that first set and said, is there exactly one arrow coming off of them? Well, in a set of ordered pairs, like this, the values of the domain are all the first coordinates in the ordered pairs. So those are the ones you're looking at. All right. So if all the first coordinates are different, then that means that there are no values in the domain that map to more than one or less than one value in the range. Right. But if you see a repeated first coordinate, and if there are two ordered pairs with the same first coordinate and different second coordinates, then that's not a function, right? Then you'd have an element in the first set that corresponds to not exactly one element in the second set. So in a set of ordered pairs, if each first coordinate, right, the x coordinate, is is paired with a different if each first coordinate, I'll say, is uniquely paired with a second coordinate, a second coordinate. In other words, no repeating first coordinates. Right. Now you can have functions where the first coordinate's repeated, just so long as the second coordinates, like if I had -3, 3, and then the ordered pair -3, 3 again, well, -3 wouldn't be corresponding to a different element. It would be just still corresponding to the number 3. So if I do have a repeat first coordinate and the second coordinates are different, then it's not a function. Right? Then you're actually having a value in the domain that corresponds to more than one value in the range. Right? So looking at this picture here with the set of ordered pairs, see, -3 in the domain corresponds to 3 in the range, and that's it. Right? I'm not seeing any other ordered pair where -3 is the first coordinate. So -3 corresponds to exactly one element in the range. Same thing for -2. negative 2 in the first coordinate, negative 2 in the domain, corresponds to positive 2 in the range, and I'm not seeing any other ordered pair with negative 2 as the first coordinate. So negative 2 does correspond to exactly one element in the range. Negative 1 corresponds to positive 1 in the range, and negative 1 doesn't correspond to anything else. So negative 1 corresponds to exactly one element. 0 in the domain corresponds to 0 in the range, and again, there's no other ordered pair with 0 as the first coordinate, so 0 corresponds to exactly one element in the range. And finally, 1 in the domain corresponds to 1 in the range. There's no other ordered pair with 1 as the first coordinate. So 1 corresponds to exactly one element in the range. This is a function. Every single first coordinate is corresponding to exactly one second coordinate, exactly one element in the range. So yes, this relation is a function. Okay, and since it is a function, right, we're asked to say if it is a function, state the domain and range. The domain, remember, is the set of all the first coordinates, the set of all the inputs, all the elements that actually correspond to something in the second set. So that's all the first coordinates here, right? So it's the set with negative 3 in it. Negative 2 is a first coordinate, that part of the domain. Negative 1, 0, and 1. And then close the set. Those 5 numbers are in the domain. And the range, recall, is the set of all the second coordinates, or all the outputs, if you want to call them that. All the elements in the second set that are actually, dependent upon elements of the first set. So I'm seeing, this is a set, so little curly braces, right? The number 3 is in there. 2 is a element that's mapped to or corresponding to negative 2. 1, 0 is a second coordinate. And then, 1 again, but there's no need to write 1 again. I've already mentioned that 1 is in the range from this ordered pair. So there's no need to repeat anything. Just close the set. These 4 numbers are in the range. Great. Now, if you didn't see that, right, if it's a little trickier maybe with all the numbers, you like pictures, you can always draw a mapping. Right? You can always do a mapping. I'll do that off to the side here. Especially when there's only a finite number of ordered pairs, like there's only 5 ordered pairs here, so making a mapping wouldn't be too terribly difficult. So I have this box, where I put in the elements of my first set, all the first coordinates there. Negative 3 is there, negative 2 is there, right? Negative 1, 0, and 1. Again, I like to put little dots so I can see where the arrows are coming from. And then a box over here for all the elements of the second set, right? All the second coordinates. Got 3, got 2, got 1, and got 0. And again, I don't need to write 1 again, right? I've already mentioned that 1 is a second coordinate, here. So no need to write 1 again. And then the arrows indicating the relationships. So negative 3, we said, corresponds to 3, right? So negative 3 in the first set corresponds to 3 in the second set. Negative 2 corresponds to 2 in the second set. Negative 1 corresponds to 1. 0 corresponds to 0. And 1 corresponds to 1 again. There's 1 over there again. But look at every element in this first set, right? Every element in the domain has exactly 1 arrow coming off of it. So like in the first 2 examples of this, that's what we can look for and say, hey, yep, this is indeed a function by definition. All right. Okay, and I have just one last example here. Same kind of problem where, we're given a set of ordered pairs, a relationship between 2 sets of numbers, and asked, is that relation a function? right, by the definition of a function. So similar problem. This time there's only four ordered pairs, four relationships. So we're seeing that -3 corresponds to 2, -2 corresponds to 5, -1 to 8, and -3 to 6. Maybe, I hope you see it. There's the issue right here. There's -3 there, corresponding to 2, and there's -3 over here again, corresponding to 6. So I see that -3, corresponds to both 2 and 6 in the range. All right, that's not exactly 1, right? That's not exactly 1 value in the range. All right, and that is a problem. All right, so remember the definition of a function. Every value in the domain corresponds to exactly 1 value in the range. That is not happening here. I am seeing a repeat of the first coordinate where the second coordinates are different. So this is not a function. Right? So this relation is not a function. Now you could still list the domain and range. All right, it still has, every relation still has a domain, still has a range. It's just, they won't be considered the domain of a function or the range of a function, right? This is not a function. So if you want to list a domain and range, fine. Great. Now, if you wanted to, again, if you don't like the sets of ordered pairs, and you're saying to yourself, "Hey, there's only 4 of those. I could make a very quick mapping of this." Well, let's do that over here. All right. So again, in one box, I have the values of the first set, or my first coordinates are the values of the domain, right? -3 in that first ordered pair, then -2, then -1. And then -3 again. So again, no need to write it again. I've already stated that it's in that first set, the set of the first coordinates. And then over here another box where I list the set of the second coordinates. The values that are dependent upon values from the first box, or the range. 2 is in there, right? 2, and then 5 is in there, and then 8. And 6, and if you want to put them in order, fine, 2, 5, 6, 8, doesn't matter what really, as long as they're in the set. And then the arrows indicating the relationships that are demonstrated in this set of ordered pairs here. We have -3 corresponds to 2, little arrow there. -2 in the first set corresponds to 5 in the second set. -1 corresponds to 8. And -3 again corresponds to 6. So you see right here, just like in my second examples with the mappings, there is the issue of -3, right? -3 has, not exactly 1 arrow coming off like -2 and -1 have, but has, 2 arrows coming off of it. So it doesn't satisfy the definition. All right, there's a value in the domain that doesn't have exactly 1 value it corresponds to in the range. So again, we would say that the relation is not a function. Okay. All right. So that was those were just a couple examples where our relation was represented by a mapping, or where our relation was represented by a set of ordered pairs. We'll get into future videos where we'll see our relations represented by an equation. And we'll be asked if we have a function. We'll talk about what it means to have one variable or one quantity as a function of another variable or another quantity. And also, we'll see our relations represented as graphs and asked, do I have a function? Is this quantity a function of that quantity? All right. And as I like to say at the end of these, try your best, do the best you can to understand the material on your own. I have found that things tend to stick better in your mind. You tend to remember it better if you've taken the time and put in the effort to learn it on your own. So, read the material. Read the author's examples. Maybe even perhaps try to work out the solutions to an example before you read what the author's done. See if you can learn from some mistakes there. Practice exercises, practice problems, and try to search for answers to those if they're provided, and check yourself, see how you're doing. Don't just give up after the first attempt though. Don't get so easily frustrated. Keep at it. If after several attempts it's still not working, you're still not getting it, try reading the material again, maybe even a third time, because perhaps a second or third reading will reveal something to you that you didn't really catch the first time. Maybe you'll have one of those aha moments where you see something or something clicks the third time through, maybe even the fourth time through, that didn't happen the first time through, and it'll make working on problems that much easier. But if after several read-throughs of the material and several attempts at problems you're still not getting it, nothing's clicking, then it is not a sign of weakness whatsoever to go looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in the class that you know knows the material and is willing to help. Look for supplemental materials online on the subject. There's plenty out there, I assure you. Look for videos on the topic, perhaps such as this one, or plenty of other videos out there that are better than mine, and I know you can find them if you wanted to. But just keep at it. All right, stay persistent. Keep practicing. Keep getting better. And try to have a positive attitude as well. A lot of people go into mathematics thinking, "Oh, I've hated math my whole life and never been good at it, and I always, I hate it," and you're just going to keep hating it if you keep thinking that. And it's hard to do. I know it's hard to change your mind about something, but try to go into your math courses, your math homework sessions, study sessions with an open mind, with a positive attitude, thinking I'm ready and willing to learn. I'm happy to learn. I'm gonna enjoy learning this. Something good might come of it. And feel good about yourself. So, and try to have some fun with it. So keep practicing. Stay persistent. Don't give up. Stay positive. And I just know you're going to get it. All right, I know you'll get it eventually. And thank you for watching.